You know, deep inside every factory, on every single production line, there's this incredible high-stakes battle happening at a microscopic level. It's a constant fight against friction, heat, and pressure, and it's a fight that really determines the quality of pretty much everything we build. So let's dive into this hidden world of toolware. You might be thinking, come on, it's just a tiny piece of metal getting a little dull, right? How much of a difference can that actually make? Well, let me tell you, that tiny, worn-out edge is the exact point where precision engineering slams into economic reality. It's the literal line between a perfect component and a very expensive piece of scrap metal.
And believe me, the stakes here are absolutely enormous. We're not just talking about a simple maintenance task. This is a multi-million-dollar problem. Toolware directly hits a company's productivity, their costs, and ultimately the final quality of everything from the engine in your car to a life-saving medical implant.
Okay, so here's how we're going to break this all down. First, we'll get a front row seat to the battle itself. Then, we're going to meet the villains causing all this damage. We'll find out what makes things worse, and then we'll explore the armor, the tactics, and even the crystal ball that modern factories are using to win this fight. All right, let's kick things off with Section 1, the unseen manufacturing battle. This is all about understanding why these tiny, almost invisible imperfections have such massive, massive consequences. So here's the thing you really got to understand. Toolware isn't just one problem. It's more like a cascade of failures. As that tool starts to wear down, the surface finish on the part gets rougher, the dimensions start to get inaccurate, but what's really critical, especially for parts and things like airplanes or cars, is that it can compromise the component's fatigue life. What that really means is it weakens the part's ability to handle stress over and over again, making it way more likely to just fail unexpectedly down the road. All right, so we get why this matters. Now let's meet the culprits. Welcome to Section 2, Meet the Wear Villains. See, to fight an enemy, you have to know it. And toolware isn't just one thing. It actually shows up in a bunch of different forms, and each one has its own unique signature.
So our number one most wanted villain is flank wear. Just picture the side of the cutting tool, the part that's constantly rubbing against the freshly cut surface. That's the flank. And abrasion, which is basically a grinding process on a microscale, just gradually wears that surface down.
And this is a perfect look at that domino effect. As that flank wear gets worse, friction just skyrockets, which of course generates more heat. The surface of the part you're making gets rougher, and just like a dull kitchen knife that can't cut a tomato anymore, the more it wears, the faster it keeps wearing out. Okay, next on our list, we've got a totally different kind of villain, crater wear. This doesn't happen on the side of the tool. It happens on the top face, where that hot metal chip is sliding across. Under all that intense heat and pressure, tiny bits of the workpiece can literally weld themselves to the tool, and then rip away, taking a little piece of the tool with them. This process carves out this distinctive little concave crater.
Oh, and the gang's all here. You've also got things like notch wear, which is this really concentrated damage right at the edge of the cut. And then there's built-up edge, or BUE, where material literally piles up and welds itself right onto the cutting tip, which completely messes up the tool's geometry and makes it way less effective. Okay, so we've met our villains. Now what's feeding them? What's making them so strong? That brings us to Section 3, the speed and heat culprits. These are the forces that just put tool failure into overdrive. Think about it like this. In any machining job, you've basically got three main knobs you can twist. There's cutting speed, which is how fast the part spins or moves. There's feed rate, which is how fast you push the tool into the part. And then there's depth of cut, how deep you go. These three things control how aggressively you're cutting, and they have a massive impact on how fast your tool wears out.
And this is where it gets really interesting. There's a clear hierarchy here. While all three of these things matter, the research is crystal clear. Cutting speed has a way bigger impact on tool wear. But why? Well, the faster you go, the more friction you create. And that friction generates an incredible amount of heat. And heat, well, heat is the absolute arch nemesis of tool life. Managing your speed is the single most important part of this whole equation.
So, that's the perfect lead-in to Section 4, armor, coatings, and materials. If speed and heat are the attackers, then this is all about the first line of defense that we build right into the tool itself.
Modern cutting tools are just technological marvels. They're often covered in these ultra-thin but incredibly hard coatings. These are put on using super high-tech processes. Think of it like, I don't know, spray painting at an atomic level to create this perfect, super durable shell. Coatings like titanium aluminum nitride act like armor, making the tool way harder, helping it handle insane temperatures, and stopping it from chemically reacting with the material it's cutting. But it's not just about the coating, right? The material underneath that armor is just as critical. The standard workhorse is tungsten carbide. It's great for its all-around toughness. But if you're machining super hard materials, like the stuff they use in aerospace, you need something tougher, like cubic boron nitride. And for extreme hardness, like when you're cutting non-ferrous materials, nothing beats polycrystalline diamond. It's really all about choosing the right warrior for the right battle.
Okay, so we've got our warrior suited up in armor, but even the best armor needs some backup. And that brings us to Section 5, Tactics, Cooling and Lubrication. These are the active strategies we use to protect the tool during the intense heat of battle.
You could go with the most basic approach, which is dry machining. Sure, it's clean, you don't have coolant costs, but the tool just takes a beating from all that raw heat and friction. A much smarter tactic is something called minimum quantity lubrication, or MQL. This uses just a tiny, precise mist of a super efficient lubricant. It's just enough to dramatically lower temperatures, reduce wear, and give you a better service finish, all while being way better for the environment. But, of course, the innovation doesn't just stop there. I mean, we're talking about some seriously cool stuff now. Things like cryogenic cooling, which blasts liquid nitrogen or CO2 to super chill the whole cutting zone. There's even nanoparticle-enriched MQL, which adds these tiny particles to the lubricant just to carry heat away even more effectively. These are the cutting-edge methods that are just pushing the boundaries of what's possible.
All these strategies help us fight wear while it's happening. But what if we could see it coming? That takes us to our final section, the Smart Factory's crystal ball. This is where we stop reacting to wear and start predicting it before it even becomes a problem.
So how does this crystal ball actually work? It's not magic, it's data. It all starts with sensors on the machine that are constantly listening and feeling for tiny changes in force, vibration, even sound. All that real-time data gets fed into AI models that have been trained to spot the subtle signatures of a tool that's starting to wear out. The AI can then predict the tool's remaining useful life and ping an operator to schedule a change at the absolute perfect moment. Not too early and definitely not too late.
And this right here, this is the Industry 4.0 toolkit in action. We're talking about data fusion, pulling in data from multiple sensors to get a much clearer picture. We're using machine learning to not just predict wear, but to classify what kind of wear it is. Some systems even use on-machine scanners for incredibly precise measurements, which unlocks something that sounds like science fiction: adaptive machining. This is where the machine itself actually adjusts its own speed and feed in real time to make its tool last longer. It's kind of healing itself, in a way.
And you know, this quote from the research really just nails it. The entire industry is heading in this direction, this powerful combination of smart sensors and AI-driven models. It's not just about making parts anymore. It's about creating an intelligent, self-monitoring system that guarantees the highest possible productivity and quality. And all of this leaves us with one pretty mind-blowing question. As our AI gets smarter and our materials get tougher, are we getting closer to a future where we could engineer a cutting tool that is, for all intents and purposes, immortal? A tool that never wears out? Just imagine what that would mean for the future of manufacturing. Definitely something to think about.